Welcome, folks. Hi. Well, I guess it did come to pass that we don't get to see each other for a few weeks, but that doesn't mean things stop. It just means I've got to collect stuff in a different way. So, first of all, how the homework's going to work, at least for today. We'll see how it works over the next couple of weeks. But what I've done is I've put Google Forms in the classroom. Okay? And in those Google Forms, you will find that I've copied the homework questions with a space for you to write the answer. Class code's there on the screen if you're not in it, but I think everybody's in it. I really need you to do the homework as normal. Do it out on a piece of paper, show your work, you include the units, use the right sig figs, and then type them into Google Forms so I can check to see how things are going for you. Keep the paper, because I'm going to look at that as part of your notebook. So I'm looking in the notebook for the work, but I'm going to look on Google Form to see how you answered. So don't forget on the work to show your work, include the units, use the correct sig figs. Okay. For tonight, I put two forms there. One is so that you can type in the homework that's due today, and one for practicing tonight so you can turn it in before tomorrow. So with that stuff out of the way, if you have any questions, email me. I'll try to respond to them as fast as I can. And I'm looking at later setting up a session for you to ask questions on YouTube. So I'll let you know when that's going to happen. But on to the new material. Okay, so I got the combined gas law, and that deals with the situation where pressure, temperature, and volume can all change, but your container's sealed and the moles of gas doesn't change at all. The fourth part is about what happens if the moles of gas do change. There's got to be a way to calculate that. And we've actually already addressed this a little bit earlier, okay, when we talked about Avogadro's hypothesis. Avogadro's hypothesis said at the same temperature and pressure, equal volumes of gas have equal moles. Okay? Another way of actually saying that is volume is proportional to the number of molecules at constant temperature and pressure. Number of molecules is moles. And if it says proportional, it doesn't say which way, that means directly proportional. So more volume, more moles. If I want more moles of gas at the same temperature and pressure would take up more space. Okay? This is where we got the idea that 22.42 liters equals 1 mole at STP, because we picked a temperature and pressure, so temperature and pressure were constant. We picked 0 degrees Celsius and 1 atmosphere, so we can compare always at the same temperature and pressure. And that way, we got V is directly proportional to N. Okay, so again, if it doesn't say which one, it's directly proportional. And as an equation, remember what directly proportional looks as an equation. As an equation, V equals Kn. We could solve this for K, which we never do, and we'd get V1 over N1 equals V2 over N2, our normal direct proportion. Okay? But what we have to do is we have to put it into the combined gas law. So we have to decide where would we put volume in the combined gas law. Well, volume is directly related. What else is directly related? Well, volume is directly related to moles, and volume is directly related to temperature. So since it's related to temperature, directly related like temperature, we're going to put it in the same place that we do for temperature. Okay, so we do that. Temperature was on the bottom, so we put moles on the bottom. N stands for moles. N, because they picked it's a number of moles. That's why they picked N for moles. So we've added N1 and N2 to the bottoms. Okay? And of course, this works because K equals K. But now, that's everything I could possibly change. It's got pressure, it's got temperature, it's got moles. All four parts have changed. So, since that's the case, that K is really constant. It never changes. It's everything you could change. So it stops being called K and is given the letter R. R is constant. It's constant for all gases at every pressure, every volume, every temperature, every number of moles. So it's constant. So I don't need the ones and the twos. So that I could write P times V over N and T has always got to equal R. And they usually write that this way. P times V equals N times R times T. All I did was just move the N and the T to the other side. And that is called the ideal gas law. And we usually write it like this. PV equals nRT. Okay? Which is just, if I take the pressure times the volume, that's going to equal the number of moles times the ideal gas constant. That's what R is called. It's called the ideal gas constant because it's constant for all ideal gases. And the temperature has to be in Kelvin for this to work. Fact is, it's called the ideal gas law, and chemists know it's the ideal gas law, but if you ask them how to do a problem that involves using it, they'll say, oh, that's just a PIV-NERT question. So they try to pronounce it, PIV-NERT. It's really PIV equals NERT. And R is the ideal gas constant, so it really doesn't depend on anything. It's always constant. The fact is, if you use the kinetic theory, and just from just the motion of the molecules, you can calculate what the ideal gas constant should be, and it works out that the calculated one matches up with the one that we can measure. So the ideal gas constant is constant. It never changes. The ideal gas constant is always 0.0821, and then it's going to have lots of units. Liter, atmospheres on top, and mole and Kelvin on the bottoms. Needs all those units to cancel out the units from everything else. So the number makes the number proportion true, and the units make it so the units work out. So R is always 0.0821 liter atmospheres over mole Kelvin. It never changes. But now I'm writing that R equals 62.4, and I know that 62.4 is not the same as at 0.821. You said it was always constant, but it is constant. It's the same value. The difference is that instead of being in atmospheres, this one's in millimeters of mercury. Okay. So the R value depends on that. The fact is, if you multiply 760 millimeters of mercury for each atmosphere times 0.0821 atmospheres, you get 62.4. So it's the same value, it's just got a different unit of pressure. So that also means that I could use kilopascals. So R is 8.31 liters kilopascals per Kelvin mole. It doesn't matter on the bottom if it's mole Kelvin or Kelvin mole. So you'll notice that the three R values only differ in what unit pressure is measured in. So that we need an R value for each pressure. So we don't have to do a conversion factor if they give us a different pressure value, a different pressure unit. So that's it. So PV equals nRT. That gives us a new way of getting moles of gas. I can figure out moles, N, as long as I know a pressure, a volume, and a temperature. So now we're not restricted to STP. Before, if I wanted to figure out moles of gas from a volume, it had to be at STP, a cold room. Now, as long as we measure the temperature and pressure, we can figure out the moles of gas anytime by just using N equals PV over RT. So let's work out a couple examples. And I think these are on your pink sheets. So, okay. One of the things you'll notice about these examples, that they don't give you ones and twos. In the past, every time I've labeled them, I've said this is a pressure, this is a second pressure. And I had situation 1 and situation 2. This gas law doesn't have ones and twos. It doesn't tell you how it changes, it tells you what it is. That means they call this an equation of state. It tells you what state it's in right now. You don't need a before and after. So, first example. So if you go buy a 2-liter bottle and drink all the soda out of it and close the lid, how many moles of air are in that 2-liter bottle? 19 degrees Celsius is a cold room, and 747 millimeters of mercury is pretty close to what the pressure is right now. So let's look at the numbers. 2 liters, that's a volume. 19 degrees, that's a temperature. And I know that it's got to be in Kelvin, so I'm going to make that 292 Kelvin. And 747 is a pressure, and they want to know moles, which is N. Anybody know an equation with those 4 pieces? Why, yes, we just learned one. It is the ideal gas law. PV equals nRT. And I want to solve this for N, so I have to divide both sides by R and T. So when I'm done, I get N equals PV over RT. So N equals pressure, 747 millimeters of mercury, times volume, 2.0 liters, divided by R, and I picked the R that matches the millimeters of mercury. And the one that had millimeters of mercury was 62.4 millimeters of mercury over mole Kelvin. And the temperature was 292 Kelvin. So you push the buttons on your calculator. Screen fills up with numbers. I think I got 0.081994 something. And 3 sig figs, 2 sig figs, 3 sig figs. So I need 2 sig figs. And I got to remember the 0 in front doesn't count, so that's 0.082. And units. Well, liters cancel out. Millimeters of mercury cancel out. Kelvin cancels out. And all I'm left with is moles in the denominator of my denominator. So I got moles in the denominator of my numerator, which is 1 over moles, which is equal to moles. Which is good because I was looking for moles, and there's my answer. Okay. So that time they gave me pressure, temperature, and volume, and I could figure out moles. But I can figure out any of the pieces along the way. So here's the next question. If I put 1.8 grams of hydrogen in a 4.3 liter balloon at 27 degrees Celsius, what would the pressure be? So they want to know pressure. When they give me a mass, a temperature, and a volume. Well, I've got most of the pieces I need. I got volume and temperature, and I want pressure. But I need, if I'm going to use PV equals nRT, I need moles. where can I get moles from? They didn't give me moles, but they gave me grams. So I can take that 1.8 grams of H2 and turn grams of H2 into moles of H2, and 1 mole is 2.02 grams. So that is 0.091 moles of H2. Now, if PV equals nRT, and I want pressure, divide both sides by volume. That means P equals nRT over V, which is 0.091 moles of H2 times R. I have to pick an R. It doesn't matter which one I pick because they didn't tell me what unit they wanted pressure in. So I could pick any one of the three. Just to do something different, I'm going to use the one with liters. So that's 0.0821 liter atmosphere over mole in Kelvin. And the temperature, 27 degrees Celsius, is 300 K with 3 sig figs. And the volume was 4.3 liters. If you push those buttons on your calculator, 0.091 times 0.0821 times 300 divided by 4.3, your calculator gives you, with 2 sig figs and the 0.091, I get 0.11. And unit-wise, well, liters cancel, Kelvin cancels, moles cancel, and I'm left with atmospheres. And that's what R does. R has the number to make the numbers work out right, and the units to make the units work out right. So you have to pick the R that matches the units of your pressure. Your homework tonight is going to have you solve for all the pieces. I've showed you how to solve for pressure and for moles, but you could also solve for volume or for temperature. The process is the same. So tonight's homework has you practice those things. If you have any questions, drop me an email. Okay, expect to keep up along the way. We're going to build this stuff as we go. So have a pleasant day. Thanks.